Hi everyone, Mr. Rowe here. I thought I would create a video lesson for you in this new unit, and the first lesson I'm deciding to help you along with is this one on the normal distribution and normal sampling and modeling. We skipped 8.1, but basically the main message from there was you can find the probability by calculating the area under the curve. You can go back and have a look at that lesson if you want, but if I have a graph of a distribution and I want to know, the probability from, let's say, A to B, if I find the area under the curve, that would be my probability. So for some kind of bar graph, that would be easy, but if your graph takes the shape of something like this, a curve, it's going to be a lot harder. So we're going to learn how to do that. So basically, this is the normal distribution. And this kind of graph, this bell-like curve, is quite common. So think about what a graph would look like if I just took, EQAO scores or test scores. What would that look like? Think about it. You'd probably, let's say the average was around 70, you'd probably have most of the people in and around the average, a lot of people here, this is the frequency here. Very few people would do very poorly. Most people would probably come in around here, but then you'd have a couple of people who probably would do really well. So it looks something like that. Think about what a graph would look like if I just took the weights or heights, we'll say heights of grade 12 boys. Well, what would that look like? You'd probably have around 5'10", 5'11". You'd probably have just a very few very short people, but the majority of people would come in right around the average, and then you'd probably have a couple of really tall people too. But notice, here we're talking about test scores, here we're talking about weight, but the shape of the distribution is the same. And like I said, this shape of distribution shows up a lot. So that's why what we're about to do here is quite useful. So just some notation first. This distribution can be described by its mean, mu, and standard deviation, sigma. It has the mean equals the median equals the mode because it's perfectly symmetrical. The larger value of the standard deviation, as we learned in the stats of two variables, the more spread out the data is around the mean. And the smaller the standard deviation, as we learned, that means the data is more clustered around the mean. It's less spread out. So here's a visual representation of that. Here's a large standard deviation. The data is more spread out. Here's one where you have a very small standard deviation. Most of the data points are clustered around the mean. So each normal distribution here has a different standard deviation, but the values of the standard deviation scale the distribution curve. So put simply, some bell curves are more stretched or compressed compared to others, but what you're going to find interesting is the area under the curve in terms of standard deviations is going to be the same. I'll explain what I mean in a minute. So here we go. For any normal distribution, 68% of the data is within one standard deviation of the mean. So for example, let's say, I play golf. Let's say my average score is 85. I've added up all my scores, that's my average. Here I'll have a few lower scores, every now and then I'll have a few really high scores, but I'll probably be in and around this 85. Now let's pretend I had a standard deviation of 5. So what this is telling me is that one standard deviation below would be a score of 80. One standard deviation above would be a score of 90. That would mean that 68% of my golf rounds would be within the one standard deviation between 80 and 90. 2 standard deviations away, so each standard deviation is 5, so 2 standard deviations downwards would be a score between 75 and 95 in my example here. 95% of the data would be, or 95% of my golf scores would be between 75 and 95. And then if you want to take it a step further, if you want to go to 3 standard deviations, pretty much all the data will be within 3 standard deviations, 99.7. So that in terms of my golf, that would be between 70 and 100. Almost 100% of my rounds would be between 70 and 100. So again, this kind of illustrates it doesn't matter if the standard deviation is a little bit bigger and the graph is more spread out, or the standard deviation is smaller and it's clustered more around the mean. These proportions are the same. And we're going to use this fact to help us model some questions. So again, here's a little bit more of a detailed breakdown. But even more than that, we have a chart which is going to show us all the possibilities, which I'll show you in a minute. So here's just an FYI. I didn't put this on to scare you, and I'm saying we will not use, not just because we don't have time, we would never use this anyway. This is probably the scariest looking formula you'll ever see in high school math anyways. But yeah, this would be the equation of the curve of the normal distribution. We don't need to use that though, because some mathematician created a little table for us which shows us all the probabilities for all the standard deviations away, and I'll show you that chart in a second. So the area under a normal distribution is going to be 1. 100% of the data has to be there. Probabilities for normally distributed populations, as for other continuous distributions, are equal to the area under the curve. So let's just kind of think about what I talked about with the golf example. So if I were to find the area under the curve from A to B, if I wanted to know what was the probability, I would just need to find this area. So how are we going to do that? Well, there's no easy formula for calculating the area under the curve, so what we need to do is find out how many standard deviations these values are away. And we have a little formula for that. And we use what we call a z-score. The z-score is the number of standard deviations a data point is away. So again, thinking back to my golf example, if I took the score of 95, how would I determine how many standard deviations that is away from my, I believe I said my mean was 85, and my standard deviation was 5. Well, obviously it's 2 standard deviations away, but how would I get that mathematically? Well, I took my original score, which is my, x, that's my observation value. I'm going to subtract the average, so let's find out how far away I am from the mean. So in this case, I'm going to be 10. Well, 10 shots, how many standard deviations is that? Well, if each standard deviation is 5, then 10 shots would be 2. So this is going to be very useful to use because it's not always going to be a perfect amount of standard deviations away. What if I shoot like an 88 that day? Well, how many standard deviations is that? Well, I would have to put in 88. I have to find out how far away I am from the mean. So 88 minus 85 would be 3. I'd be 3 shots away from the mean. How many standard deviations is 3 shots? Well, it's 3 divided by 5 would be 0.6 standard deviations. So as I mentioned, the z-score indicates the number of standard deviations away. The distribution of the z-scores of a normally distributed variable is a normal distribution that has a mean 0 and standard deviation 1. So this is called the standard normal distribution. And the probability for all of these are widely known and will be seen on this table that I keep referring to in a minute. So a little notation for when we're talking about the normal distribution is we use a capital N, and then we put the mean and the standard deviation. So for my golf, if I were talking about my golf game, and you saw this, this would tell you that I have a mean score of 85 and a standard deviation of 5. Okay, so for the standard normal, where the mean is 0 and standard deviation is 1, you have this. So this is the key right here. Areas under the standard normal distribution are known to a very high degree and can be found on this table that I'm finally going to show you. This is the table. Okay. What this tells you is the area under the curve between 0 and whatever your z-score is positive. So due to symmetry, they don't need to give us negative because we can use symmetry to figure that out. So for example, 1 standard deviation away is 0.34 or 34%. And that makes sense because if z was 1 and this was -1, we'd have 34. This would be the 68. So in that other example I said, well, hey, what if I shoot, what's the probability I'm going to shoot, between 85 and 88, right? Well, that was 0.6 standard deviations away. There'd be a 22.57% chance. We will be using this chart quite often, so I think you'll get, if it sounds a little confusing right now, just wait till you see some examples coming up, and I think it'll make more sense. That being said, I did take the liberty of filling out this lesson in advance just because it would end up, it took me 3 hours, so I figured you wouldn't want to watch a 3-hour video, so hopefully we'll keep it a little shorter and I'll just talk through the work that I did. So how do we use that table to calculate the probability? The table that I just showed you, and I don't know why these are always cut off, but it will always show you between 0 and z. So to use the table, you search along the left to find the first 2 digits of the z-score, then top to find out. So it's going to be accurate to 2 decimal places. So just say I'm 1.47 standard deviations away. I go to the 1.4, then I go to the 0.07, so 1.47 would be this value right here, 42.9%. Alright, so let's get to it. It wants to know what is the probability that 0 is less than z is less than 1.58. So what's the probability that my z-score will be between 0 and 1.58? So you can see this is 0, the mean is 0. So here's 1.58. So they want to know what is the area under the curve here. Well, this is exactly what the table is going to show me. It's going to show me between 0 and any positive z-score. So the probability that 0 is less than z, less than 1.58, I can just go directly to the graph. So I'll show you where I got this number. So I'm looking for 1.58. So 1.58 is 0.4429. So that's where I got that from. Right? Now it wants to know what is the probability that, z is just outright less than 1.58. So not greater than 0, less than 1.58, just less than 1.58. So here's 1.58. I need to know all of this area. So we're going to be using some logic and symmetry to help us with some of these questions. Because this question isn't too much different from this other than I'm adding all of this shaded region. But because 100% of the data is under the curve, 50% is on the left side of the line and 50% is on the right side of the line. So if I need to include all this, this is 50%. So that's why I have here 0.5 plus this area here, which we calculated in the above question, 0.4429. So the total area under the curve would be 94.29%. Okay, so things are going to start to get interesting in the next example here. So now it wants to know what is the probability that z is greater than 1.58. So all the shaded regions that we're interested in, I've shaded in blue. I've tried to do some color coding to hopefully make it easier to follow along. So hopefully that works for you. So look at the shaded region I want. Well, that table doesn't tell me Z is greater than. That table is always going to tell me less than Z. Whatever that Z score, less than Z, greater than 0. So we need to dig deep here. So I want this shaded region right here. I'll highlight this in red. Well, how am I going to get that? I can't get it directly from the table. Well, what can I get from the table? I can get the green shaded region. I can get between 0 and 1.58 positive. So how do I find the red? Well, if I know that this whole side is 50%, it's going to be 0.5 or 50% minus the green. If I do 0.5 minus that green shaded region, it will leave me the shaded region that I want. So that's what you see here. The probability that Z is greater than 1.58 is 0.5 minus the green, which is the probability 0 less than Z less than 1.58. And we already know that value is 0.4429, so it's going to be 0.5 minus 0.4429, approximately 5.7%. So maybe try the next one on your own, pause the video if you need to, but it's basically the exact same. I need Z greater than 2.3. So here's the 2.3. I'm going to use the same logic here. There's no way to figure out this shaded blue region directly, but what I do know is that this is 50% of the data, and if I subtract this, it will leave me with the blue. So the probability that Z is greater than 2.3, again, it's going to be 0.5 minus the probability 0 less than Z less than 2.3 positive. This is the green, which I've now colored over in red. So if we go look at 2.3 on the table, and of course I've already filled it in, but I'll just show you again, 2.30 is 0.4893. So that's why I have 0.4893. I guess it should have been 0.4893. I guess I wrote down something a little different here. Am I on the right one? Oh, never mind. Never mind. I'm good. 0.4893. So about 1%. So there's only a 1% chance that any data distribution that follows a normal distribution, that a data point will be more than 2.3 standard deviations away. So just to put that in perspective of my golf game, I said I shoot, mean 85. What this is telling me is that 2.3 standard deviations away from this, well, 2.3 times 5 is about 11.5, so 2 standard deviations away from this, there's about a 1% chance that I would shoot higher than this. And this kind of makes sense, right? You might think, wow, that's a really low number. But really, if I average to shoot 85, how likely is it that I'm going to blow up and shoot over 100? Not to mention the standard deviation I gave myself was actually pretty low. My standard deviation could have been like 7 or 10. And then think about how high that value would be. Okay, so moving on. We might not do all these examples. They get kind of repetitive, so hopefully you get the hang of it. So I started to introduce, well, what happens when your Z score is negative? Your value is below the mean. Well, we're going to use symmetry again. So I want to know, what is the probability that Z is less than negative 1.5 standard deviations away? So this would be like me saying, what's the probability my golf score is less than 77.5. That's the probability I'm after here. So the blue shaded region is the probability that I'm interested in. Again, there's no way to get this directly from the table. So I'm going to use symmetry. This is a symmetric curve. So this blue shaded region, the probability that z is less than negative 1.5 is going to be equal to this green shaded region, which is the probability that z is greater than 1.5. So if I can find the green, that's going to equal the blue, which is what I want. And in the last example, we already found the green several times. We did 0.5, which is the entire red region, minus the red, 0 to 1.5 positive, 0 to 1.5 positive. So it ended up being 0.5 minus, and then if I go to 1.5, 1.50, it's 0.4332. I get approximately 6.7%. All right, next. What is the probability that z is greater than negative 1.5? So again, you can see the blue shaded region that I'm interested in. Well, this part's pretty easy. It's just going to be 50% because I have to include all of this. And then how am I going to get this piece of the blue shaded region? Again, no direct way to get it from the table because it's a negative z-score, but that is going to be equal to what I've shaded in as green. The probability 0 is less than z is less than 1.5 positive. So we've already looked up this value. It's about 43%. So it's actually going to be the 0.5, which is all this side, plus 43% for this piece right here. So I found the green, which equaled this shaded blue part, and then I'm including all of this, so I added 0.5. What is the probability that z is greater than negative 2.5, less than 0? So this is just straight symmetry. I needed the blue, so I flipped it to the positive z-score symmetrically. I want to find the probability between 0 is less than z is less than 2.25 positive. So the green equals the blue, and I can easily find the green from looking at the table. So this is the last time I'll refer to the table. I've already filled in all these values, so hopefully you know how to use the table now, and we'll just take my word for it that I put these values in correctly. So 2.25 positive, 2.2, 0, 1, 2, 3, 4, 5, 4, 8, 7, 8. Just confirm that. And that is what I wrote down. And finally, this little piece here, I want the probability z is less than negative 2.25. So I just want this little blue shaded region here. No direct way to get it. So I use symmetry. I say, oh, well, that's going to be equal to the probability that z is greater than 2.25. And I can't get this directly, so I need to do 0.5 minus the probability 0 to 2.25 positive. So I do the red, or 50% minus the red gets me the green, which equals the blue, which is what I want. All right, a couple more examples of this where I think I'll do a range, and then we'll move on to a couple more examples, then we'll be done. So now I want to know, what's the probability that my z-score is going to be between 1.2 z-scores and 2.65 z-scores. So again, I want the shaded blue region. Well, how am I going to get this? My table will only give me 0 less than z less than a positive z-score. So what I need to do is find between 0 and 2.65, which would give me this entire green shaded area. So that's not hard to find. I can find the whole green shaded area, but I don't want all that area. I want just the blue. So what I want to do is subtract the red shaded area. So that's what I have up here. The green, which is all of this, if I subtract the red, will equal the blue, which is what I want. So the green is between 0 and 2.65, 0 and 2.65, which is about 49.6%, minus the red, which is between 0 and 1.2 positive, which is about 38.49. So if I subtract those, if I take all this green and subtract the red, I'll be left with the blue, which is approximately 11.1%. The second last example here has one value that's negative and one that's positive. So again, a little bit of symmetry here. I'll break this into two parts. The blue shaded region, which is the total region that I want, is going to be the green. Well, that's easy enough. That's just going to be between 0 and 1.85 positive. 0 and 1.85 positive, 46.8. But how am I going to get this other piece, this little blue? It's in the negative. So I switched it over to the other side using symmetry, and that becomes the red. So the red equals this blue piece over here, which I then add to the green to get the total area. Hopefully that made sense. So I wanted this whole blue shaded region, so I found the green. Easy enough. And I wanted this piece too, so I used symmetry, found the equivalent shaded region, which is the red one here. 0 is less than z less than 0.55 positive, and then I added them together. And lastly, just in terms of going through these examples before we get into word problems, I have two negative z-scores. And hopefully, as you can pick up by now, anytime you have a negative z-score, you have to flip it using symmetry so the z-scores are positive. So if I want between negative 2.9 and negative 1.4, that's going to be the same as finding between 1.4 and 2.9. The blue shaded region equals the green shaded region. And we did an example like this, I believe, right up here. So how am I going to get the green shaded region? I'm going to do between 0 and 2.9, 0 and 2.9, which is the green. That would give me all of this. I'm going to subtract the red, which is between 0 and 1.4. That, if I subtract the red, that gives me the green, which equals the blue, which is what I want. So hopefully that went well, because you're going to have to use these skills to answer all the word problems. And we'll look at one now. So, Julie is 168 centimeters tall. In her high school, boys' heights are normally distributed with a mean of 174 centimeters and a standard deviation of 6 centimeters. What is the probability that the first boy Julie meets at school tomorrow will be taller than she is? So we're going to draw a sketch to kind of show what's going on here. So again, think about it, heights. This would take the shape of a normal distribution. As I already demonstrated, you'd have a few short guys, but the majority of them would probably be close to around the average, and then you'd have a couple of people out here who are probably pretty tall. So here's Julie. If the mean is 174, the mean goes right through the middle of the normal distribution, and here's the notation up here. Mean 174, standard deviation 6. Here's Julie at 168. She's below the mean. So they want to know what's the probability that the next boy she sees will be taller than her. So it wants the probability that x is greater than 168. What is the probability that x is greater than 168? So what we're going to do is this process called normalization. We're going to normalize this. We don't have a table that's going to show me, standard deviations of 6 and means of 174. We only have a table that shows us mean 0, standard deviation 1. But because I showed you that proportionately these areas are the same, we're going to convert these values into z-scores. So 168, all that really matters to me is how many standard deviations away is that. So I'm going to use my z-score formula to convert this into standard deviations, and then I can use the table to make the approximation. So Julie is 168 centimeters tall. How many standard deviations is that? So 168, I subtract the mean. She's minus 6 away from the mean. And each standard deviation is 6, so she's exactly -1 standard deviations away. So really what this question is asking, or you can calculate as an approximation, the probability that the next boy she meets is taller than 168 is going to be equal to the probability that z is greater than -0.1. These two areas are the same. So if I can find this area, this is a really good approximation for the area in the word problem. So, do we know how to find this based on all those examples we just went through? Hopefully the answer is yes. How do I find the probability that z is greater than -1? Well, it's going to be 0.5 because I'm going to include all of this shaded region, plus I need this piece. I'm going to use symmetry and find the probability that 0 is less than z is less than +1. I'm going to get this piece, which will equal this green slice over here, add that to 0.5 and get my total. So looking that up on the table, you get approximately 0.34. So there's about an 84% chance that the next boy she meets will be taller than her. So what I'd like you to do ideally is try this next one on your own. So again, you can pause the video. It's very similar to the one above it. You're going to draw out the graph of the real world scenario, then you're going to draw out the normalized version in terms of standard deviations. So pause the video if you want, try this question, then you can unpause it as you need to if you need help or you get stuck, or you can just check at the end to see if you got it right. So similar question, the Aero Chocolate Bar Factory, you see the candy wrappers say 50 grams of chocolate in each bar. Well, they're probably not all exactly 50 grams. So you would probably have a very, you'd probably have a normal distribution that looks like this. The mean is 50, but you'd probably have some Aero bars that weigh more, some that weigh a little less. It'd be very rare for one to weigh a lot more or a lot less. So you'd have a normal distribution that probably looks something like this. So the actual masses have a normal distribution with mean 50.5 and standard deviation of 0.6. They want to ensure that each bar contains at least 49.5. So they don't want to have a scenario where there's too little chocolate. What percent of bars do not have this much? So again, here's the scenario, and I've kind of stretched it out a bit. Even though it probably looks more like this, I've kind of stretched it out just because it'll help us visualize this. I have a normal distribution with a mean of 50.5 and a standard deviation of 0.6. I want to know what percent of bars do not have at least 49.5. So what's the probability that x is less than 49.5? So I need this blue shaded region. So what I need to do, again, there's no table that's going to show me this, but there is the table that's going to show me the standard normal distribution. So if I can figure out the z-score that goes along with this, I can use that to find the green shaded region, which is going to be approximately the same as the blue. So how many z-scores away, or how many standard deviations away, is the 49.5? So 49.5 minus the mean, divided by standard deviations. So it's going to be -1.67. So what this question is really asking is what's the probability that the z-score that you're going to be less than -1.67 standard deviations away. So how do I get this green shaded region? I'm going to use my symmetry. I'm going to try to find the red shaded region. What's the probability that Z is greater than 1.67? Because if I find the red, that equals the green, which will equal the blue, which answers my question. And we've already done examples of this where we try to find this positive Z score greater than value. So probability that Z is greater than 1.67, it looks like I'm going to have to take, I'll go purple here. Here's the 0.5, 50%. I'm going to subtract out this piece that I don't need, and that'll leave me with the red, which equals the green, which equals the blue, which is what I want. So it's going to be 0.5 minus, and the piece I don't need is between 0 and 1.67. Because the table will only tell you between 0 and positive Z. So I take 0.5, I subtract out this 1.67. When I look on the table here, do it one more time, 1.67 is 0.4525. Okay, so I do 0.5 minus 0.4525, you get 0.0475 or 4.8%. So this red percentage, even though it looks like more, just because of the way I've drawn it, is really only about 5%. And this red equals the green, which again equals the blue. So that's about it. So when you're done going through this lesson, here is your suggested homework.